The periodic table is split up into different regions called blocks, and these blocks are called the S, P, D and F blocks. They take their name from the outermost occupied subshell, or sometimes called sublevel. So for all of the elements in the S block, their outermost electrons are in an S orbital. If an element's outer electrons are in a p subshell, they are in the p block. This region in the middle of the periodic table here is the D block, and it's in the D block that we find the transition metals. The top row of the D block of the periodic table contains 10 elements, all of which are metals whose outer electrons are in a D subshell. The transition metals are the elements titanium through to copper, and they have some distinctive properties that make them quite different to the metals in groups 1 and 2. When working out the electron configuration, we need to remember that we fill the lowest energy sublevel first before moving to putting electrons into the next sublevel. And sublevels are split into orbitals, which are filled singly before electrons start sharing orbitals. So as an example, let's look at argon. It has got an atomic number of 18, which means it's got 18 protons and 18 electrons. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. For D block elements, it's important to remember that we fill the 4s subshell before moving on to fill the 3D. So for titanium, as an example, which has got an atomic number of 21, so that means it's got 3 more electrons than argon has, its outer electron configuration is 3d1, 4s2. And that means that the 4s subshell is filled, and we're in the process of filling the 3d subshell. Remember, the D sublevel has 5 orbitals, each holding 2 electrons, so potentially up to a total of 10 electrons. And we can see this pattern if we look at the top 10 elements in the D block from scandium through to zinc. You can see that I'm showing the electron configuration of argon as a shortcut, so I don't have to keep writing it all those 10 times. And I'm just focusing on the 3D and the 4s subshells, so we can see how those are filled. And you can see that the pattern of filling the 4s before the 3d is kept to mostly across the top row of the D block, with the exceptions of chromium, which has a precisely half-filled D subshell and S subshell, and copper, which has an entirely filled D subshell and a partly filled S subshell. And those are exceptions that you need to know, where those elements are slightly more stable as a result of that particular electron configuration rather than the one that you might expect. The definition for transition metals is to do with their ions that they form. Metal atoms generally form positive ions by losing electrons, and another rule for the D block elements is that they lose the 4s electrons before the 3d. Transition metal elements, for instance those between titanium and copper, get their characteristics because they form at least one stable ion with an incomplete D subshell. So for instance, titanium can form the stable ion titanium 3+, and so it will lose 3 electrons from its outermost shells, and that will give it the electron configuration that I'm showing here. And you can see that it has lost the S electrons, and it has a partially filled D subshell in the 3d1 configuration. Here are examples of stable ions for the other 9 elements in the top row of the D block. You can see that for the ions titanium through to copper, the examples that I'm showing are stable ions with an incomplete 3D subshell. Scandium and zinc are exceptions. Scandium typically only forms a 3+ ion, which means its D subshell is in fact empty. Zinc typically only forms a 2+ ion, and it loses its 4s electrons to do so, and so the 3d subshell is in fact entirely full. Therefore, scandium and zinc are not considered to be transition metals because they do not form stable ions with an incomplete d subshell. Transition metal characteristics of elements titanium to copper arise from an incomplete d sublevel in at least one stable ion. These properties include complex formation. The formula of a complex looks something like this one containing copper ions. More about this in a moment. Transition metals have variable oxidation states. For example, iron can readily form iron 3+ and iron 2+ ions. Transition metals can form coloured ions. For example, iron 3+ forms a yellow solution and iron 2+ forms a green solution. Transition metals also display catalytic activity. For example, nickel is the catalyst when hydrogen is used in the reduction of aldehydes and ketones. Since scandium and zinc do not form stable ions with an incomplete d sublevel, they are not transition metals, and so they do not have these properties. For instance, they generally form white solids and are colourless in solution. A complex is a central metal atom or ion surrounded by ligands, and a ligand is a molecule or ion that forms a coordinate bond, also known as a dative covalent bond. And it does this by donating a pair of electrons into an empty or partially filled d orbital of the metal. And so the formula of the complex might look something like this, with a copper metal, that's the electron pair acceptor, also sometimes called a Lewis acid, and we can see that the ligands on this occasion are water molecules, the electron pair donors, and so to be a ligand something must have an electron pair to donate, a lone pair, and this is sometimes referred to as a Lewis base. And you can see in this formula there are actually 6 water ligands. And the coordinate bond itself comes from a lone pair on the oxygen atom in the water ligand, and that electron pair is donated to the metal copper. Unless we're specifically told to do so in an exam question, you won't be expected to show the lone pair and the arrow in an exam question. They're typically more interested in showing the shape of the complex. And so the complex that I've shown here would have this octahedral shape, and you can see that the way I'm showing the bonds, we're giving some acknowledgement to the three-dimensional space filling of these ligands. If the complex carries an overall charge, like this one I'm showing here, it is referred to as a complex ion. And most commonly in exam questions, you will encounter complexes as complex ions. And when you write the formula or show the shape of a complex ion, it's really important to show the formula or the shape inside square brackets like I'm doing here, and have the overall charge on display in the top right-hand corner. The coordination number of the complex is the number of coordinate bonds to the central metal atom or ion. Most common coordination numbers are 6 and 4. And the most common complex you'll encounter here is the hexa-aqua complex, like the one I've shown here, which is called hexa-aqua copper 2. And in general, we'll see the formula of the complex with, I'm showing here M for any generic metal, 6 water ligands, and typically the complex will have a 2+ charge or a 3+ charge. And this is the complex that forms when any metal compound dissolves in water. Ligands are classified by the number of coordinate bonds they can form with a metal ion. Monodentate ligands can form 1 coordinate bond to a metal ion. And the term dentate comes from the Latin word for teeth, and it describes how ligands bite onto a metal ion, forming, in this case, a single coordinate bond. Examples of monodentate ligands include water, ammonia, and the chloride ion. And you can see from the diagrams that I'm showing here the shapes of these ligands and the lone pairs that are available to form coordinate bonds. The water ligand and the chloride ion have multiple lone pairs, but they can still only form one coordinate bond each. And that's because their geometry prevents multiple lone pairs from bonding to the same metal. Ammonia and water are a similar size and uncharged. The chloride ligand, as well as having a negative charge, is larger than the ammonia and the water, and this affects the shape of complexes with chloride ligands. Transition metal ions commonly form octahedral complexes with small ligands, for instance with water ligands and with ammonia ligands. I'm showing the formula of a complex ion here. We've got copper and we've got 6 water ligands and a 2+ charge overall. This will form an octahedral shape like I'm showing here. You need to be able to draw complex ions like this, giving a clear indication of the spatial arrangement of those bonds and those ligands. We need to show the square brackets around the outside and the overall charge that's being carried by this complex. Another example is this cobalt complex with 6 ammonia ligands. Again, we've got a 2+ charge overall, so again we need the square brackets with the 2+ on the outside and a clear indication of the octahedral shape, and all the bond angles need to be 90 degrees. Transition metal ions commonly form tetrahedral complexes with larger ligands, and that's because there's not enough room for 6 ligands to fit. They literally take up too much of the available space. An example of this is the chloride ligand. And so in the complex with copper ions, we can only fit 4 chloride ions around the central copper ion. And so we get a tetrahedral shape, and the bond angles will be 109.5 degrees. And so this copper complex with CuCl4 as its formula needs the square brackets around the outside and the 2- charge overall. Bidentate ligands are able to form 2 coordinate bonds to a metal ion, and there are 2 bidentate ligands that you need to know. The first is the ethane dioate ion, which has got the formula C2O4, and it's a 2- ion. And you might find this ion in something like ethane dioic acid or sodium ethane dioate. When we see the displayed formula for this ion, you can see the 2 oxygen atoms that have the lone pairs through which the 2 coordinate bonds can form. And when we make a complex ion using these ligands, we end up with 3 bidentate ligands typically bonding to the metal, forming an octahedral complex. And so the formula for the complex ion would be Fe and then C2O4 inside rounded brackets with a little 3 afterwards to show that there are 3 of this bidentate ligand. And then we need the square brackets around the outside, and this ion has a 3- charge overall, meaning that this was an iron 3+ ion before those ligands bound together to give it an overall charge of 3-. And we can see from this diagram here the octahedral arrangement, those 6 coordinate bonds around the iron ion, and so the coordination number is 6 as a result of that. And here are the 3 ethane dioate ions in those 3 positions around the octahedral complex. The other bidentate ligand that you need to know is ethane 1,2-diamine. And this is its structural formula here. And it's only when we see the displayed formula or the skeletal formula for this ligand that we see the 2 points that coordinate bonds can form from on these 2 nitrogen atoms this time. And again, 3 of these ligands would bond to an iron ion, for instance, and we would get the complex like so, Fe, and then the formula for the ethane 1,2-diamine ligand. We've got 3 of them, and overall this time I'm giving it a 2+ charge because I'm saying that the iron is a +2 ion. And since this is really quite a long formula, the ligand is sometimes abbreviated to En, instead of writing the formula for ethane 1,2-diamine as I did at first. And if we were abbreviating it like this, the formula would be significantly easier to write. We'd retain the square brackets and the 2+ charge overall, and of course the symbol for iron is unchanged, but that structural formula for the ligand is removed and we replace it with the En, and we still need those 3 afterwards to show that there are 3 of this bidentate ligand. Multidentate ligands form many coordinate bonds to a metal ion. One example that you need to know is the EDTA 4- ion. EDTA is an abbreviation and it stands for ethylene diamine tetraacetic acid. But as a ligand, it will be the 4- ion, and here is its structure as I'm showing like this. You won't be required to remember the formula or to draw it, but you need to know that it's a multidentate ligand, and you need to be able to identify where it can form coordinate bonds. And it can in fact form 6 coordinate bonds. And you could be asked to circle the atoms with lone pairs that it could use to form those coordinate bonds. And because it can form 6 coordinate bonds, there must of course be 6 atoms to circle. 2 of them are the nitrogen atoms in the middle, and the other 4 are these 4 atoms that I'm showing here, the oxygen that are carrying the negative charge, and I'm showing them with the lone pair here. You also need to be able to write formulae and equations working with complexes containing the EDTA ligand. For instance, we've got 2 formulae for complex ions here, one with an iron metal and one with copper. For the iron, the overall charge is -1, and so that means iron plus EDTA 4- will have a -1 charge overall. Therefore, iron minus 4 is equal to -1, and so the iron metal must have a +3 charge on this occasion. And since the overall charge for the copper complex is 2-, copper must be +2 as a result. You need to be able to draw the shape of complex ions. Typically, there will be an octahedral or tetrahedral shape, and it's most likely that it will include the ligands mentioned in this video, but it might be for something unfamiliar. And complex ions can contain more than one different type of ligand. An example of this is the compound that I'm showing here, and it's an ionic compound with this complex and a chloride ion. And since the chloride ion is a negative ion, the complex must be positive overall. And so we've got the chromium metal and 6 monodentate ligands, 4 ammonia and 2 chloride ions. That means that this will be a complex with an octahedral shape. And so we've got our central transition metal, we've got our 6 coordinate bonds around that metal, and I'm showing the spatial arrangement as well, and then we need to add our 6 ligands, add the brackets, and then put in the overall positive charge. You could also be asked to work out the oxidation state of a metal in a complex ion. For instance, for this one here, the overall charge of the complex is +1. We've got a chromium metal, we've got 4 neutral ammonia ligands and 2 negative chloride ligands. And so that means that chromium plus 4 lots of 0 plus 2 lots of -1 equals +1 overall. So chromium plus 0 minus 2 is equal to +1, and that means that the oxidation state of the chromium must be +3. Sometimes complex ions can have a linear shape. And an example of this that you need to know is Tollens reagent. And this is what you get when silver ions with a charge of 1+ combine with 2 neutral ammonia ligands. And they take up the linear shape because the electron clouds in those 2 coordinate bonds move until they're as far apart as possible in 3-dimensional space, which is 180 degrees. When this complex is used as Tollens reagent, what we get is reduction of the complex to metallic silver in the presence of aldehydes. To make this happen, you would take a water bath, because this only works when the chemicals are warmed. You'd get a boiling tube of one compound, perhaps the aldehyde, and then another with the ketone. You'd add Tollens reagent to both of them, and the aldehyde would be the one that gives you the silver mirror that forms. The ketone would display no visible change. The equation for this reaction has got the aldehyde reacting with 2 of the complex of Tollens reagent in alkaline conditions, so we need 3 OH- ions, and that gives us the oxidized form of the aldehyde, which would be the carboxylate ion. We'd get the silver that has been reduced from 1+ to silver 0. We've got our 4 ammonia, and we've got 2 water as our final product. We also need to know that Tollens is produced when the silver halide precipitate dissolves in the presence of ammonia solution. For example, silver chloride will dissolve in dilute aqueous ammonia, and silver bromide, the cream precipitate, will dissolve in concentrated ammonia, and the complex ion that forms is Tollens reagent along with the bromide ion. Complexes can display stereoisomerism. This is where two things have the same structural formula but a different spatial arrangement. Octahedral complexes can display cis-trans isomerism with monodentate ligands. Remember, examples of that are water, ammonia, and the chloride ion. Cis-trans isomerism is a form of geometric isomerism, and in this the ligands differ in their positions in space relative to each other. Cis-trans isomerism follows the same principles as EZ isomerism, but cis-trans isomerism is used when we have two identical ligands, and these ligands might be next to each other or they might be opposite each other. So in this first complex, we're showing the cis isomer, which is equivalent to the Z isomer. And I'm showing here this copper complex with 4 water ligands and 2 hydroxide ligands. And this is the cis isomer because the 2 hydroxide ligands are next to each other. Whereas, if the 2 hydroxide ligands are opposite each other, we will have the trans isomer of this complex, which is equivalent to the E isomer in EZ isomerism. It isn't only octahedral complexes that display geometrical isomerism. Platinum-2 complexes adopt a square planar geometry rather than tetrahedral, since this is more stable due to the electron configuration of the platinum ion. And square planar complexes can also display cis-trans isomerism. The most common example of this is Cisplatin, which is an anti-cancer drug. It has the formula PT-NH3-2Cl2, which means that there are 2 neutral ammonia ligands and 2 negative chloride ligands. And the platinum ion has a +2 charge, and so therefore overall this complex is neutral. In cisplatin, the 2 chloride ligands are together next to each other, and in the stereoisomer transplatin, the 2 chloride ligands are opposite each other. And so both of these stereoisomers have the same formula, but they have a different spatial arrangement. And it is only cisplatin that is able to act as the anti-cancer drug. The transplatin has the wrong arrangement of its ligands. Octahedral complexes can display optical isomerism when there are at least 2 bidentate ligands. Remember, optical isomerism is where you get 2 non-superimposable mirror images, and the bidentate ligands that you need to know are ethane 1,2-diamine and the ethane dioate ion. So as an example, if we had a cobalt 2+ complex with 3 bidentate ethane 1,2-diamine ligands, one of the optical isomers could look like this. You can see here these are the 3 bidentate ligands. The spatial arrangement is all important here. Those wedges are coming out towards us and those dashed lines are moving away from us. If we put a mirror here and we draw the mirror image of this complex, right now these 2 complexes look identical. But if one of the isomers, for instance the one on the right, is rotated 180 degrees, 2 of the bidentate ligands now have different spatial arrangements to the other optical isomer. If we consider this bidentate ligand at the top here, this bond is pointing upwards and the other bond for the bidentate ligand is pointing away from us. If this isomer rotates 180 degrees, the coordinate bonds become upwards and towards us. And then the one at the bottom currently is shown as one of the coordinate bonds going downwards and the other one coming out towards us. But if this rotates 180 degrees, the bonds will become down and away from us. And so whilst they look the same, their spatial arrangements are different. You need to be able to draw cis, trans, and optical isomers when given the formula for a complex. And when drawing optical isomers, you would only need to draw the two diagrams that I'm showing here either side of the mirror, not the rotated complex. And you also need to be able to describe the type of stereoisomerism shown by different molecules or complexes. In a complex, one ligand can be replaced by another, and this is called a ligand substitution reaction. Exchange of the ligands ammonia and water occurs without change of coordination number. For instance, if we have the hexa-aqua-cobalt-2 complex that I'm showing here, and we add ammonia to it, perhaps by adding concentrated ammonia solution, what happens is all 6 of those water ligands get replaced by 6 ammonia ligands. And so we end up with a new complex, which is still octahedral, still got 6 ligands attached to the central cobalt, but now we've got 6 water molecules that have been removed from that complex and replaced by ammonia. Sometimes the substitution of ligands may be incomplete, and the example of this that you need to know is when hexa-aqua-copper is reacted with an excess of ammonia. On this occasion, only 4 water ligands are replaced with 4 ammonia ligands. And so the equation looks like this, with the complex being reacted with 4 ammonia molecules, and we end up producing this new complex and 4 substituted water ligands. The exchange of water ligands by a chloride ion can involve a change of coordination number. For instance, if we add concentrated hydrochloric acid to metal aqua ions, we get a change of coordination number from 6 to 4. You can see this in the equations that I'm showing here. If we start with a blue solution of hexa-aqua-copper 2+, and we add concentrated hydrochloric acid, what will happen is all 6 of those water ligands will be removed from the complex, and they will be replaced with 4 chloride ions as ligands instead. And so the equation shows the 4 chloride ions being added and the 6 water molecules being removed. And of course the complex changes as a result. And as a result of the coordination number changing, the shape of the complex changes as well, going from octahedral to tetrahedral. And remember, this happens because the chloride ion is a larger ligand, and so only 4 chloride ions can fit around the copper. This works in the exact same way if you have a different complex, for instance a pink solution of hexa-aqua-cobalt-2 reacting with concentrated hydrochloric acid will produce a blue solution of this tetrahedral cobalt with 4 chloride ions as ligands, and 6 water molecules will be removed. And that's the same thing for when this iron 3 complex is reacted. We add 4 chloride ions and we produce the tetrahedral iron chloride complex, which is still a yellow colour in fact, and then we remove the 6 water ligands. Bidentate ligands and multidentate ligands replace monodentate ligands from complexes much more readily than one monodentate ligand replacing another. And this is known as the chelate effect. And the word chelate comes from the Greek word for chlor, which is the perfect analogy for how these ligands work. They grip the metal ion at multiple points, forming a much more stable complex. And this is what we're referring to when we mention the chelate effect. The explanation for this effect comes from thermodynamics and free energy. If we remember the free energy equation, we can see that we've got delta G equals delta H minus T delta S. And delta G is therefore affected by 2 things, the enthalpy change and the entropy change. And in order for a reaction to be feasible, delta G needs to be less than or equal to 0. So in terms of enthalpy change, if there is no change in coordination number, that means we'll have the same number of coordinate bonds being broken as are being made. And in general, coordinate bonds are similar in terms of their enthalpy, so there will be an enthalpy change that is very close to 0, and so we can say that delta H is negligible. When it comes to the entropy change, if a substitution involves an increase in moles of particles, this will be a positive entropy change. In other words, there will be an increase in disorder. And since delta H is effectively 0 and delta S is positive, when we work out delta G, we're subtracting a positive number away from 0, which means that the free energy change is going to be negative, and this ligand substitution is going to be feasible. As an example, if we see this hexa-aqua-copper complex reacting with 3 bidentate ethane dioate ligands, we've got 4 particles in solution in our reactants. If all of those water ligands get substituted out, and we end up with 7 particles in solution as our products. And so this is an increase in disorder, a positive entropy change. We see this even more if we've got our hexa-aqua-copper complex and the EDTA ligand, this multidentate ligand. We have only 2 particles in solution in our reactants. But then when we make the new complex and we substitute out all 6 of the water ligands, we end up with 7 particles in solution. And so this is a very large increase in disorder. And so this reaction, this ligand substitution, will happen very readily. And it's worth noting that if the forward reaction has a negative delta G, the reverse reaction will have a positive delta G. And this means that the reverse reaction is less feasible. And that's what we mean when we say that the product is very stable. It will not readily turn back into the reactant. Heme is an iron 2 complex with a multidentate ligand, and it's a crucial example of ligand substitution that takes place in our bodies. The heme group is comprised of an iron 2 plus ion and a porphyrin ring, which works around the square plane of this iron 2 plus ion and forms 4 coordinate bonds through nitrogen atoms to the central ion. And then actually there are 6 coordinate bonds overall. This one going downwards is to a protein called globin, which is how haemoglobin gets its name. And the coordinate bond going upwards is actually to an oxygen molecule. And this makes up haemoglobin, which is the structure where we've got oxygen at the top. And this oxygen binds reversibly to the iron 2+. That's really important because what that does is it allows the oxygen to be transported in the blood, and then the coordinate bond breaks, releasing the oxygen so it can be used in aerobic respiration. And a molecule of water takes its place. And so this is an example of reversible ligand substitution, as one ligand, the oxygen, is swapped for another, the water. And once the oxygen has been substituted out, we have a new molecule called deoxyhemoglobin. And that's when we've got the water in this top position instead of the oxygen. You need to know that carbon monoxide is toxic because it replaces oxygen coordinately bonding to the iron 2+ in haemoglobin and substituting the oxygen out. This carboxyhemoglobin is a very stable complex, and carbon monoxide is much more strongly bonded. And so this ligand substitution is irreversible without medical treatment. And so it reduces the ability of the iron 2+ to carry oxygen around the body, and that's what makes the carbon monoxide toxic. Cisplatin is an anti-cancer drug, and it works by preventing DNA replication. This is a molecule of cisplatin here, and you can tell it's the cis stereoisomer because the 2 chloride ligands are next to each other. After cisplatin enters a cell, a chloride ligand is replaced by a water ligand, and this is an equation for it here. You can see that there are 2 chloride ligands in the first complex, and afterwards one of them gets substituted out and replaced with water. And then the water molecule is replaced by a new coordinate bond, forming between platinum and a nitrogen atom in a guanine nucleotide in DNA. And then the remaining chloride ligand is also replaced as another coordinate bond forms between platinum and a nitrogen atom in a second guanine nucleotide adjacent to the first. You can see here the platinum still coordinately bonded to those two original ammonia molecules, now bonded to the two guanine nucleotides. Here's the guanine base and the deoxyribose sugar and the phosphate group in one strand of DNA, and then in another strand of DNA we have a new guanine nucleotide with a further coordinate bond forming between a nitrogen atom and the platinum. These coordinate bonds stop the DNA strands from separating and replicating. You need to be aware that cisplatin is toxic, and it can cause side effects because it enters both healthy and cancerous cells. However, cancer cells absorb more cisplatin due to their higher blood supply, making them more affected. And so despite the risks, the benefits of treatment far outweigh them.